The control room screen says this water tank is holding at 82%. The independent gauge says it is overflowing. Both systems are online. So where did truth split? A joint CISA advisory updated on July 22 describes ongoing attacks against internet-connected PLCs. At one U.S. victim, actors downloaded a malicious project that kept downstream ladder logic but added logic overriding instructions for safe operating parameters. Watch for 4 things: the normal control loop, the project file attack path, the misconception that hides the change, and 5 defensive checks that do not treat a live plant like an ordinary IT lab. A programmable logic controller, or PLC, sits between the process and the machinery. It reads inputs such as pressure or level, evaluates its control program, then writes outputs to pumps, valves, and relays. That program can include ladder logic and reusable modules. Rockwell calls those modules add-on instructions, or AOIs. Other platforms use terms such as function blocks. They package logic for reuse, which also makes changes inside them worth reviewing. A second path feeds the operator's view. PLC tags reach an HMI or SCADA display, where values, alarms, and status become the screen people trust. Normally, physical truth and operator truth agree. The common mental picture is a destructive attack that replaces everything and crashes the controller. The observed project did something quieter. Enough normal ladder logic remained to look plausible, while added logic overrode the safe result. The chain began with reachable, misconfigured PLCs. The actors used manufacturers' engineering software from leased infrastructure, then transferred controller project files to actor-controlled systems. That can resemble legitimate maintenance because the tool and project format are legitimate. After extraction, the project becomes the attack surface. CISA and the FBI identified modified or deleted logic, including reusable AOIs, followed by malicious project interactions at the controller. The trick is not noisy code everywhere. It is control at the decision that matters. The advisory also reports disabled shutdown and alarm logic, plus manipulated HMI and SCADA data. That creates 2 failures at once. The process may enter an unsafe condition, and the expected warning or displayed value may no longer tell the operator. Consider a fictional tank. Above 90%, close the inlet. Above 95, stop the pump and raise a high alarm. Now add an illustrative override at the final valve command, mask the alarm, and clamp the displayed level to 82%. The original comparisons can still evaluate correctly, yet they no longer control what moves or what the operator sees. This example is not a reconstruction of a victim system. Here is the catch. Normal-looking logic is not proof of control integrity. Trace every path that can write the actuator command, and verify the path that produces the displayed value. Those are separate integrity boundaries. Break the chain at access first. Remove direct internet exposure, place remote access behind a secure gateway and firewall, and review available logs for unexpected engineering sessions and traffic on the OT ports identified in the advisory. Coordinate changes across IT, OT, the asset owner, and the integrator. Then compare the live controller project with a protected, approved, current baseline. Review the main routine, reusable AOIs or function blocks, alarm and shutdown paths, and every write to critical outputs. A stale or untrusted baseline can give false confidence. Treat the HMI as one observation, not ground truth. Corroborate it with controller diagnostics, independent sensors, historian records, and physical process indicators. A mismatch is evidence to investigate, not automatic proof of compromise. So remember, control the access, diff the project, trace the final writes, and verify the screen independently. Use the 10-question PLC integrity check in the description, and subscribe for more mechanism first explainers.